Hello everyone, I am Indrasish. I'll be presenting my work titled Statistics Aware Low Overhead Training and Rate Implications for RIS-Aided Systems. Now, this is the outline of our talk. We will first give an overview of what are we trying to do here. Then we'll discuss our system model, our novel channel estimation scheme, and its mean square error and rate implications. We'll end our talk with a few key takeaways. Okay. Now, this reconfigurable intelligence surface consists of this passive elements which can induce a phase shift on the incident signal. What we want to do here is we want all the signals that's coming from all the RIS elements to come to the receiver coherently. Hello everyone, I am Indrashish. Today I'll be presenting my talk. Hello everyone, I am Indrashish. I'll be presenting my work titled Statistics Aware Overhead Training and Rate Implications for RIS-Aided Systems. This is the outline of our talk. Uh, Before we jump into our actual talk, let us give an overview of what are we trying to do here. So this reconfigurable intelligence surface consists of these passive elements which can induce a phase shift on the incident signal. What we want really is we want all the signals coming from all these RIS elements to combine coherently at the receiver. And to do this, we need to set up the RIS phases so that it can cancel out the phases that had been induced by the user to RIS and the RIS to AP channel. And to do that, we need to know the channel state information of these both channels. Now, you might ask me, is this the only way to do this? No. There are lots of other schemes. First one is this instantaneous CSI based scheme where you estimate the channel and configure the RIS accordingly. For codebook based schemes, you choose RIS configuration from a predefined codebook and the code word that gives you maximum receive signals, you choose that. Statistical CSI based scheme completely, demolishes this idea of training or estimating the channels. It configures the RIS based on the channel statistics. In this work, we focus on instantaneous CSI based schemes. Why? Because it gives high beamforming gain. But the problem with the scheme is it has large training overhead. All the conventional schemes like on-off scheme or DFT training scheme all suffers from this. There are lots of overhead reduction techniques that has been proposed in the literature. For example, grouping based schemes, machine learning based schemes, and then there is this reduced subspace least square based schemes, uh, for which the pilot overhead is rank of the channel covariance matrix. Now, what we want to do here in this work is we want to cut down this pilot overhead even more. And the idea is to exploit the spatial correlation. And we exploit this spatial correlation and we derive the optimal pilot powers and RS configurations during training for our proposed method. And we analyze the rate implications and we finally show that our scheme needs far fewer pilots than several benchmarking schemes. And this is even lower than the effective rank of the user to RS covariance matrix. And this effective rank is something even lower than rank. Now, let us come to a system model. We have considered a uplink communication model where the user to RIS channel is non-line of sight and random, and the RIS to AP channel is line of sight and deterministic, and the direct path is blocked. In the first tau interval, within the correlation interval of tau c, we send the pilots and then we send the data. Now let us look into the transmission protocol in a little elaborate way. In the first tau, in time intervals, we send the pilots with pilot powers P1 to P tau, and the corresponding RIS configurations are phi 1 to phi tau. Based on them, you estimate the non-line of sight random user to RIS channel because we don't need to estimate G because it's deterministic. And we set up the RIS phase accordingly and send the data. Okay. Now the question is, how do you figure out this pilot powers and the RIS phase configurations during training, right? So we determine them so that it minimizes the mean square error in estimating the channel for a given pilot power budget. And here is our uh, optimization problem. Now we transform this optimization problem and restate it in terms of this x, which includes not only the pilot parts but also the RIS configurations and the RIS to UV channel user channel. Now this problem is non-convex and a QCQP problem, so we can't solve it in a normal way. We have to do something else in order to solve them. And to do that, we propose a two-step approach. In the first step, we relax the unit modulus constraint and get a solution. And in the second step, we do a least square fit between the solution of the first step and the actual uh, thing. And we get the solution in terms of the eigenvectors of the channel covariance matrix. And both these steps have closed form solutions, so complexity is really low. Now let us look into the mean square error and the rate implications of this proposed scheme. First, we deal with mean square error, and here we plot the normalized mean square error as function of the number of pilots for different SNR. We see that the MSE decreases and reaches the floor as you increase the number of pilots, and the floor is reached well before not only the rank but also the effective rank. And the point where floor is reached, you after that you don't need to send more pilots because the MSE is not going to change. And as we decrease the SNR, uh, this 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 number of pilots decreases even more. Now, we saw this thing from a mean square error perspective. Now, let us look into this thing from a rate perspective. And why do we want to do this? Because for rate, there is always a trade-off between training overhead and the effective SINR. So we derive a expression for rate that captures the price paid for training and the estimation error. Now, this expression is not mathematically tractable since we are going for some low complexity solution. We try to lower bound it, which can be, you know, which can have a closed form approximation, and we maximize this lower bound on the rate to get the optimal number of pilots and pilot data bars, right? Now, here's a numerical result related to the achievable rate. Uh, as a function of the number of pilots. As you increase the number of pilots, first your SINR increases. After a certain point, it reaches a peak, and then your uh, overhead kind of pulls your rate down. Hmm? And the point where it reaches a peak is your optimal pilot length. And we saw that it's less than the required to reach the MSE floor also. So we can go even lower than that point. Now, we claimed a lot of things, but how were we in front of other existing schemes? In this numerical result, we plot our result and benchmark it. We plot achievable rate and benchmark it with Gini-aided scheme, the RSLS scheme, and DFT training with and without grouping. And we show that our post scheme achieves higher rate than all the practical schemes. This Gini-aided scheme is a scheme which assumes full CSI availability, so it's kind of a uh, upper bound to the all practical schemes. So obviously, to our proposed scheme will do worse because we are considering estimation error and no CSI availability. So So, as for key takeaways, we have proposed a novel training scheme that exploited channel correlation. We have jointly designed the optimal pilot powers and the RS configurations to lower the MSE. We showed that the our scheme has better rate than several benchmarks, with optimal pilot length being smaller than not only the number of RIS elements but also the rank and effective rank of the channel covariance matrix. As for future work, you can go for multiple antenna system at the base station or the AP and non-LOS model for RS to AP channel. Uh, Here's the publications that we have done. Uh, the first one we have published in ICC this year in May, and an extended version of this work, which deals with this non-LOS thing for RIS2 AP channel, is included in this journal, which we have submitted, and it is under review right now.